All right, now for some additional examples for the chain rule. Up to this point, we've taken a look at some of the more simpler functions as far as what's on the inside. Well, sure, we've had to use the sum and difference rule or the power rule or the product or quotient rules, but they've all been semi-simple functions. And now we're going to advance on to the trig functions, which can cause us a little bit more consternation, so be very, very cautious and be very careful as to what they're asking. As we take a look at the first one here, we're asked to find the derivative of y with respect to x when y is cosine of 3x. Now recall that cosine and sines and tangents and cotangents and all their other buddies are all functions in and of themselves. And so if they happen to have something inside that is not just plain old x, then that inside thing is also its own function. And so this really is a nested function. So let's go ahead and take that derivative. The chain rule says, first we need to take the derivative of the outside, which is the cosine. The derivative of cosine is negative sine. And then we put the stuff that's in there. We put that inner function right back in there just as we did it with the others. And then we have to multiply that by the derivative of what's on the inside, or the angle. In this case, it's 3. And so y prime is actually negative 3, the sine of 3x. There's that one. On the second example, we have the inside being squared. Be careful here, sine is not being squared. The angle is being squared. And so when we find the derivative with respect to x, we take the derivative of the outside. The derivative of sine is cosine. So we have cosine of pi x squared times the derivative of the inside, which the derivative of the inside, if we kind of cover up cosine for a second, it's the derivative, so it's 2 pi x times the derivative on the inside of that, which is pi. Okay, so there was like a triple nesting there. And so this is actually equal to 2 pi squared x cosine of pi x squared. All right, so let's take a look at a third example here, and we're looking at 4 times secant squared x. And so just as we have been, we need to just first operate on the outside. Now this 4 is a constant, and I can bring that out of the derivative. Or I can simply leave it there. And I choose to leave it there and kind of combine that rule with the power rule, so that when I bring down the 2, it's not just 2 or 4, it's 4 times 2. And so this is going to be 8. Okay, so I take the derivative of the outside, which is 8 secant x, times the derivative of the inside, which in this case is going to be secant. The derivative of secant is secant tangent. Secant x tangent x. This is the derivative with respect to x of secant x. Okay, that inside function. You can also think of this as 4 times secant x squared. That's kind of what that square means. It's just more, it's convention to write it in this form. I don't know why. I think the other form is actually a little bit nicer as far as telling you what's going on, but I don't get to make the rules. So as we're doing this, we take the derivative of the outside, and so we brought down our 2, then we had secant x to the first, and so that's where we got our 8 secant x. Multiply it by the derivative of the inside. The derivative of secant was in fact secant x tangent x. And so recombining those together, we have 8 secant squared x tangent x. All right, let's go ahead and continue on, and this will be the final example in this video. We've got f of t is equal to 3 times times secant squared of pi t minus 1. And so we really are having about a three-tiered chain rule here. We have an outer function, which is the square. We have an inner function, which is the secant. And then we have an inner function, which is pi t minus 1. Okay? So we want to be very, very cautious how we do this. Here we go. Again, if you want, you can break this up in the multiple thousands of derivatives I've taken. Eventually, I found out that it was actually easier to run them in the chain rule because I could constantly embed them and embed them and embed them. I just separate them by parentheses. I found that to be easier rather than separating them into separate functions and then trying to remember which derivative is where, and I actually got more screwed up. So in this case, I'm going to take it as one entire derivative. F prime of t equals the derivative of the outermost, the square. And so we bring the 2 down. So we have 3 times 2, which is 6. And that's times, or that's secant. We reduce the power to 1. So that's pi t minus 1 times the derivative of what's inside times the derivative of secant, which is in fact secant tangent. Secant x, or pi t minus 1 tangent pi t minus 1. All right, derivative of secant is secant tangent. So we've taken the outside, we've taken the inside, and now we take the derivative of the third. So the derivative of secant squared is 6 secant, or 3 secant squared was 6 secant. Then we take the derivative of secant, which is secant tangent. Then we take the derivative of what's inside here, which is pi, just pi. Okay, so let's make sure that we haven't lost ourselves here. F prime of t is equal to 6 secant times secant tangent, which is 6 secant squared pi t minus 1 times tangent pi t minus 1 times pi. So just cleaning it up one more time, we have 6 pi secant squared pi t minus 1 tangent pi t minus 1. Again, if you need to break it up, okay, I would choose to break it up this way. Take and make it's secant squared, and I'll say of u. Then you have secant of x. Then you have pi t minus 1. So those are your 3 nestings. So you have to take the derivative of this, then the derivative of this, and the derivative of this, and essentially you multiply them all together. Okay, just don't forget that u stood for something. Okay, it stood for this this pi t minus 1 in that case, and then x stood for pi t minus 1 in the next case, and then finally you have pi t minus 1. So just walk through it very slowly. Watch this video a couple times from this point, and see, just make sure that you're catching each one of those little steps.